Hey guys, today we're going to talk about line of best fit. When we collect data, so if we have, say we're a scientist and you're collecting data and you want to plot the data on in a coordinate plane, we're just going to show the first quadrant here. When you actually start plotting the data, it's not always going to make a nice even line. Okay, so this is an example of data that's been collected that has a positive correlation. Okay, if you notice, if I made a line and I went through the middle of this all right here, it would be a positive slope. A negative correlation would look like this. So with the positive, as your input values are increasing, your output values are increasing. And now with a negative correlation, as your input values are increasing, your output or your y value is decreasing. So that's a negative correlation, so a negative slope. And then if data values don't have any correlation, they're just kind of all over the place. Okay. So we're going to be using Desmos today, the graphing calculator, and I'm going to show you how to do that. So when data shows a positive or negative correlation, we can model the trend in data using the trend line. So the trend line is also known as the line of best fit. So you should be looking at your notes for 33A here. Okay, so if you notice, this data is shown for electric hybrid cars sold. So in the year starting in 2000, so 2000 would be right here at the origin, and then it goes out to 2004, 2008, 2012, and 16. We got some sample data. Now, the line of best fit is the line that kind of goes in between the best fitting line, all right? Might not go through some points, it takes the average of all the points and it makes the equation of the trend line or the line of best fit, okay? So right now this is a little complicated, but let's figure out the slope here. We have 2 points that are actually on this trend line that we can use. We've got the point 16,500 and 250. So finding our slope, we would just say 500 minus 50, and that would be divided by 16 minus 2. So our slope would actually be 450 fourteenths, which is 225 sevenths. Okay, so there's our slope. All right, if we did point slope form, maybe we picked this point to use, the 250, and we put it in. We can get our point slope. And we're not going to have to do this just yet, but I just want to show you how it gets kind of complicated with a fraction. So this would be, we would say y minus 50 is equal to the slope, which is 225 sevenths, okay, times x minus 2. All right, after you distribute and bring the 50 to the other side, your equation is going to be y is equal to 225 sevenths x minus 100 sevenths, okay? So if we wanted to then approximate the number of electric hybrid cars sold in 2010 would be right here on the graph. We can kind of go up right here and see it's going to be a little bit above 300, okay? But we can use this equation that we came up with, 225 over 7x minus 100 sevenths, and we can let our x be our input. Since it's 2010 and we started at 2000, we're going to let x be equal to 10. All right, so when we change our input value to be the 10, we just substitute it in, okay? And when we do the math, we're going to find out that our y is approximately 307.14, so we're going to say it's approximately 307, okay? So when it kind of shows on the graph, it's a little bit more than 300. Okay, a linear regression is the method used to calculate the line of best fit. Okay, it's very complicated, so we actually use a calculator to do it. It's the most precise way to do a linear regression. Okay, so linreg is actually the function on the calculator that you use. And on the TI-84 calculator, which we're not using this year, but y equals ax plus b is really the line of best fit right here. The a is the slope, okay? It's just a different letter, okay? And it gives it to you in decimal form. This r value that the calculator will give you is called the correlation coefficient, and it's a number that falls between -1 and 1, and it indicates the direction and strength of the linear relationship. So if the r is close to the number 1, all right, then it's a strong positive correlation. But if it's close to -1, it's a strong negative correlation. And if it's close to 0 in the middle, okay, that would show there's a weak correlation. All right. So here's what we're interested in. We're interested in using Desmos. So this says the table shows the amount of time required to download a 100 megabyte file for various internet speeds. Assuming the trend continues, how long would it take to download the 100 megabyte file if the internet speed is 75 kilobytes? Okay, so here are internet speeds would be our inputs. So we have speeds of 35, 40, 45, 50, 55, 60. And then our outputs would be the time it takes. So in minutes. So 6.65, 5.82, 5.17. Notice our times are going down. So this would be a negative correlation. As our speeds are increasing, our time to download is decreasing. So we eventually want to find out how long it's going to take for 75 kilobytes per second. So we're going to start by using Desmos. Okay, so I want you to go to Desmos and start graphing. Okay, so let's see if I can get this to line up here. Move this over. Okay, hold on, get this over. It's a little hard to tweak it. Okay, it's got to line up a little bit better. Okay, hold on. Okay, there we go. Okay. So, and I want to make it a little bit, let's graph it, there we go. Okay, so to take the data, okay, this is going to be important. I want you to hit this plus button, okay, this plus button right here, and then we hit the table. This is going to allow us to put in a table of values. So our input values are our X values, and we're going to put in the number 35. I need my, okay, 35. Okay, for our input value. Okay, hold on. It's stuck there. Okay, we've got 35. We've got 40. Okay, we've got 45. We've got 50. We have 55. And we have 60. Okay, now our output or our Y values, they have to correspond. So according to the table, it's 6.65. Okay, 5.82. Okay, we've got 5.17. We've got 4.65, 4.23, and 3.88. Okay, so if you notice, okay, I'm going to zoom out. We can probably see it on the graph. Actually, it's a little bit further over. So notice we can see them on the graph over there. Okay, all right, so we want to see the line that's going to go through those, okay? So to do that, and this is really important, notice our column labels are X1 and Y1. That's important because if you're using Desmos and yours, when you added your table, maybe it was the second table, it might say X2, Y2, okay? But we're going to put it in our slope form, so it's Y1, okay? And then we're going to use the little tilde button, shift tilde. So Y1 tilde, and then we've got MX1 plus B, okay? So notice we just made our little, I'll show you right here, I'll pull this over, and you can see we made a line going through our data points, okay? So in the statistics portion, you can see our parameters are M is negative 0.1. That's our slope, okay? So we're going to round it to the nearest tenths, and our y-intercept right here, it crosses at 10.26. So we can use this information and immediately write an equation of a line, okay? Now, if I want to look over here at my correlation coefficient, the R value, it's negative 0.98, so it's very close to -1. So it's a good, solid negative correlation. Okay, so again, we're going to take the M value and the B value, and we're going to write them out. So we've got we've got our M is going to be negative 0.1. and our B is 10.3. So when we write the equation of the line of best fit, it's going to be y is equal to negative 0.1x plus 10.3. All right, and then it says, step 3, now we want to figure out, okay, what's the output value when our input is 75? So we're just going to let our x be equal to 75. And we're going to plug it in and figure out our y. Y is equal to negative 0.1 times 75, okay, plus 10.3. Now we do our order of operations, multiply, and then we add, and we get a final answer of 2.8 minutes. So we're using Desmos to come up with the equation of the line of best fit. All right, so if I looked at number 1 here, I want you to try it. Okay, so put in your values, but before you do that, okay, when you go back to Desmos, make sure, okay, that you delete your table and your formula there, and you start over again. Okay, so for each one, keep starting over. You add your table in. All right, and then your input values, your kite's price is going to be your input value, and the quantity is going to be the output values. So when you look at this, okay, your input values, let's move this over again, okay, your input values will be your X values, your price, and your quantity is your output, your Y. So after you put those in, you can pause the video right now and put it in. You're going to find out that your M value is equal to negative 0.5, and your B value is equal to 28.5. So the equation of the trend line, or the line of best fit, would be y is equal to negative 0.5x plus 28.5. All right. How many $40 kites would the store sell? So say we decided to up the price to $40. So what this is doing is the store records the price of kites in dollars and the number of kites sold. So as we increase the price, the number of kites sold goes down. Okay, so it's a negative correlation, and that explains our negative slope. So now we're just going to let our x be 40. Okay, and when we put x is equal to 40 in, we get y is equal to negative 0.5 times our 40 plus 28.5. Okay, so your y is going to be equal to 8.5, so we're going to say approximately 8 kites. Okay, so I want you guys to go ahead and look at number 2 and try it. Okay, again, pause the video if you need to. I'm just going to give you the answers for it. So for number 2, your M should be equal to 3.2. Your B should be equal to 17.8. All right, so the equation would be y is equal to 3.2x plus 17.8. And if you looked at your R value, your R actually would have been equal to 0.9978. So it's a very strong positive correlation. So positive correlation. Okay, so is it a good is the function a good model? Yes, it is, because it's very strong, very close to 1. All right, so let's now predict. Anytime you see predict, it's saying, okay, let's let x be 30. So y is going to be equal to 3.2, all right, and then times 30 plus 17.8. Okay, and then when we do that, we end up with y is equal to 113.8. Okay. All right, so now we're looking at a different scenario. Temperatures at different times of the day are shown. Enter the data points in Desmos and list the ordered pairs. Okay, so you can put these in as your input would be the time of day. Okay, so you might have 12 a.m., 4 a.m., 8 a.m. Okay, but as we increase, okay, the time, what's going to happen is the temperature is going to start going all the way up until the middle of the day, and then it's going to go up, and then it's going to start coming down. So the temperature, the relationship between temperature and time is throughout the day, the temperature increases. Once the sun sets, the temperature begins to drop. So would a linear model be a good fit for this data? We're just going to say no, okay? Because temperature increases and then decreases. So that's not a good linear relationship, okay? This is something we'll probably cover a little bit later when we do quadratic regression. So we're not going to worry about this one right now, okay? All right, so number 4 is a table that shows the number of active red woodpecker clusters in part of the DeSoto National Forest in Mississippi. Write an equation that models the number of active clusters as a function of the number of years since 1990. Now this is important because whenever we have a year, all right, we don't want the year to be the input value as far as putting in 1992. we want to have it smaller, so it's the number of years since 1990. So our year here was actually going to be 2 because 1992 is 2 years away from 1990. And then we put in 3 and 4 and 5, 6, 7, 8, 9, and 10. Okay, so put the data in like that for your input values. Once you do that, your M, okay, you can pause it again and try it, but your M is 3.7, your B is 12.5. So the equation would be y is equal to 3.7x plus 12.5. Okay, all right, now you try it. Try number 5 on your own. Again, pause the video and then see what you get. Your M should be 1.6, your B should be 2.3. So your equation is 1.6x plus 2.3. We don't have to make any predictions. All right, then you guys are going to do the same thing for number 6. Okay, put it into Desmos. If you do that properly, your M would be about negative 4.4 and your B is equal to 14.7. Okay, again, we're just practicing using Desmos. Clear out those tables each time. Then you write the equation of the line, negative 4.4x plus 14.7. All right, and then the last one that we have, number 7, it says the table below shows the median floor area of a new single-family houses in the United States during the period 1995 to 1999. So since 1995 is the period that we're starting with, we're going to set that to 0. 96 is 1 year away, 97 is 2, 3, 4. Okay. So we're going to find the equation that models the data. So the median floor area, even though these look like dates, they're not dates, it's the area square footage. So you're just going to leave that as 1,920, 1,950. So the only ones we're going to get rid of are the dates again. Those are the only ones we change. Okay, so again, you can pause the video, and when you come back, you should have the equation that models the data as y is equal to 26.6x plus 1,921.4. Okay, it says predict the median floor area of a new single-family house in 2025. So now we want to know, what about 2025? Okay, well, 2025 is 30 years away from 1995. So we need to let our x be equal to 30 in that case. Okay, that's important. When we do that, we plug it in. Y is equal to 26.6 times 30. And then we add it to the 1921.4, okay? And we end up with y is equal to 2,719.4 square feet. Okay, all right, that's it. I suggest you get through the homework as much as you can, and remember, you're going to need Desmos for it.